The first thing to say is that none of us really know what time is. We can only bring our own experience and our own perceptions to the table, and my perception is as a physicist, and there are certain ways that we treat time in our the theories that we develop and in the equations that we write. Man has contemplated time for centuries, and this is a quote from St. Augustine's Confessions. What then is time? I know well enough what it is, provided no one asks me. No word could be plainer or more commonly used, yet its true meaning is concealed from us. We have still to find it out. We use the word time in everyday speech, but somehow we can't, it has this sort of essence that we can't touch, it's not, and yet we're quite sure that it's there. And somehow at the psychological level, there's this sort of separation between something that we know that's there, but we can't actually sort of say precisely what it is, versus the attempt as a physicist to try and get it down on paper, to actually sort of make it something that is real and something that we can use. So these are my list of the types of time, the context in which we use the word time in speech, perhaps. We have some notion of psychological time. It seems to flow differently for different people and for the same person at different times. I know if I'm been a bit naughty and I've had too much to drink, my perception of time changes. Time seems to go more slowly after I've had a few drinks. I think, oh, it must be bedtime now, and I look at the clock and it's just sort of 8:30. Biological time, of course, can relate to things like our heartbeat and our physiology. Time seems to have an arrow. It seems to go in one direction. So, whereas in terms of space and time do become quite intimately linked, as I'll touch on a bit later, it is different in character to space. So it seems to flow in one direction. So I can say that I'm travelling north or south, but it makes no sense to say I'm travelling towards yesterday. So we speak of the arrow of time, and similarly we talk of the causal ordering of events. So it is always the case, it seems, that causes precede effects. So we, you know, if I launch something into the air and then it comes down, I catch it, and it all seems to follow some causal sequence. Can that be interrupted in some way? Physics has certain things to say about that, but it seems to be, at least from our everyday experience, that the causal ordering can't be interrupted. We speak about the beginning of time, which of course has philosophical and religious overtones, but again, physics has a very specific notion of Big Bang, that about 14 billion years ago the entire universe was compressed, and we speak of a beginning of time. And so in many respects, the physicist thinks of time as a kind of a coordinate, and I'll say a bit more about that as well. But it's not, but I stress, it's not the same type of coordinate as, say, space or X, Y, and Z or whatever. Historically, we've tried to marry our perception of psychological time to ones that appear to be regular in nature. And so we talk about the time it takes for the Earth to rotate, which is a day, the Moon to go around the Earth, which is a month, and the Earth to go around the Sun for a year. And that historically then develops into the notion of a calendar, as the kind of temporal sequencing of events that we can look up onto a table, which we call a calendar. I'm quite interested in this sort of paradigm, if you like, because the notion of a calendar obviously goes way, way back over the centuries, and we've had calendars for that long. And yet it's independent of the correctness or otherwise of the processes that we're using to measure time. So, for example, in prehistory, we thought that the sun went round the Earth, and that was just as viable a marker for time as the picture that we have now, that the Earth goes around the Sun. All that matters is our physical, our psychological perception that it appears to be periodic, and we take that as our kind of a marker and set it down. And while we're on the topic of a heliocentric or a sun-centered system versus an Earth-centered system, of course, that was overturned by Copernicus and then Galileo. and Galileo somewhat fell out with the Catholic Church on the issue. After Galileo came Newton. In fact, Newton was born the same year that Galileo died, and he was the first person to really wrestle with how time could be implemented into some sort of physical or physics theory. And he was a genius, of course, but his aim was to set things down logically in a famous book called Principia. And he has to start with some basic assumptions. And one is that he introduces the notion of absolute time. So whereas I'm speaking about the psychological time can be different for me or for you or for me at different times depending on whether I'm pissed or not. And here Newton proposes that there is some external reality called absolute time, God's clock if you will. And he says that absolute true and mathematical time of itself and from its own nature flows equably without regard to anything external, and by another name is called duration. Relative, apparent and common time is some sensible and external, whether accurate or unequable, measure of duration by the means of motion, which is commonly used instead of true time. So he makes this clear separation between our perception of how things move, if we've got some motion of some body or whatever, to him is that is just a representation of something that ultimately can be mapped back to what he calls true or absolute time. This is my attempt at sort of taking what Newton said and then sort of giving a perspective of what time might mean to a physicist who's looking at Newton's mechanics today. This is kind of one of the best ideas I can think of, that time is defined so that motion looks simple. What do we mean by constant speed? The very terms that we use in the expression of the law seem to relate to time in some sense. So what do we mean by constant speed? It's our perception that it seems to be rolling off at a continuous rate. And what does simple mean when I say that time is defined so that motion looks simple? Well, I think these ideas can actually be linked together in a simple way. And the diagram that I think of is this one, in which space, I call x, is on the horizontal axis and time is in the vertical axis. Now, if I were to actually take out some clock, I could actually sort of mark off. So this is my clock. I could actually, and I take out a ruler. I've got a ruler in my bag somewhere, so I could mark off the positions, and I've got the time. I could make a set of observations of where that body is at different times. I could make those notes. I could translate it into a plot on the diagram, and if that it turns out to be straight like that, I think I could reasonably say that the motion is simple. This line is straight and it's not curved, and I think that it's constant because it seems to be equal amounts of space in equal amounts of time. So that for me is the one way of looking at Newton's idea that that a body can moves with constant speed if no forces act. But there's a problem, and it kind of cuts to the heart, it seems to me, of what we mean by this sort of plasticity of time. Now, it may be that I'm using a poor clock. In fact, I forgot to nick one from the lab, so I had to buy this on my way here, and this was a very cheap clock. So how do I know that the second for which that it goes for the first part of the motion is the same duration of time as for when it reaches some other position? How do I know that it's the same extent of time for at different times? If all I've got are my rulers and my clocks, I've got no way of knowing whether my clock is a good clock or a bad clock. And so this is the kind of, the issue we have to kind of penetrate. And Newton's answer was to say that actually all of these possibilities have to be referred to some absolute time, or God's clock, if you will. Now that changed in the early 20th century with Mr. Einstein, who had a radically different idea of the notion of time. Einstein, in his theory that he introduced in 1905, had two very important ideas. And the first was that no one can tell the difference between moving with constant speed or whether you're at rest. So if I'm in a car and I'm moving along the road, but all the windows are blacked out and it's all sort of very carefully insulated, so I can't feel the vibrations of the car. I've got no way of telling on the basis of experiments that I'm moving as compared with when I'm at rest. All people, all observers, if you like, it's the ultimate democracy that I can say that I'm moving and you're at rest, or you can reach the converse conclusion. And the second great idea, which is actually related to the first, but not in an obvious way, but so we separate it off and make it a different idea, and that is that the speed of light is the same for everyone. Now, this is a very kind of counterintuitive idea that the speed of something is the same even if you're in motion. We think of, say, if we're on a train and if I'm running along with my ball on a train and then I throw the ball, you think that the ball is going faster because you add up the train's speed to the ball's speed. And to some extent that is true. That is the way mechanics works at low speeds. But as you approach the speed of light, it looks very, very different. And in its extremist case, the speed of light itself is actually the same for everyone. Time reverts to being this kind of personal time. So whereas, I said at the beginning about psychological time and this sort of external Newton's absolute time, that branching off, with Einstein's relativity, time again acquires this sort of personal character, that it's different for different observers. And it really is different. It's not just a kind of, this is the way the world is. So sound waves travel in air. I'm talking to you, the air molecules are wiggling, and you get the sound coming to your ears and you hear me. Water waves travel in water. Light is different. Light travels in nothing. And it's because it travels in nothing that there is nothing to gauge it against. And so when I put my observer, my little chap here, looking at the light wave that's traveling in nothing, there's nothing. He can measure its speed and it will be at 30 million meters per second.
Does it travel in air?
Yes, it travels in air and it slows down a little in consequence. But the point is that light has as a wave phenomenon, has the possibility to travel in nothing. I can make a clock using light. I could take a ruler like this, and I could put a mirror at the top and a mirror at the bottom, and I could just send a pulse of light up and down like that, okay? It would tick pretty quickly. So I can imagine the tick being the upward bit and the tock being the downward bit. But that would be a perfectly good clock. It's an excellent clock, actually, much better than this one. Now imagine that I take this clock on a journey. I take it whizzing off like this. I'd get a different, you in your seats would get a different picture. I'm travelling off to the right. The light pulses in this clock would take a different trajectory. They'd follow that kind of triangular path. The light would have to go further, according to you. It goes further, but the speed of light is constant, so it must take longer. The tick and the tock become longer. It's, instead of going tick-tock, 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 it becomes tick-tock. I don't think we're uncomfortable with the notion that the moving light clock apparently shows a longer time, because it's obvious, because it's gone on a longer path. But the profound insight is that everything must go slow. If I'm running along with my light clock like this, all biological processes, my heart, everything must go slow because to maintain synchronism with my light clock. If it didn't, I'd be able to tell that I was moving and that you were stationary, because I would have my grotty clock, for example, and I'd have this light clock. If there was no synchronism between my processes, my heartbeat and so forth, and the light clock, then I would know that I was moving because they'd step out of sync. The only way out is to repeat what I said a moment ago with Einstein. I can't tell that I'm moving, so my act of going like this must be the same as if I were in your frame with my light clock just sitting here, and we don't expect any slippage between the two measures of time when we're just sitting here. So there's this profound consequence that time really is dilated and changed as a consequence of going further. So light travels further in B, and therefore we perceive, if we're at rest, we perceive that clock to be going slower. And it's not an illusion. The world really, really is built like this. If you have two twins and one of them gets into a space rocket and runs away, so it's exactly the experiment that I just described, and then comes back, now you have the possibility of comparing the two watches. Okay, so whereas just now I was talking about sort of me running away with my light clock and you perceiving it as going slow, and then on the converse that you were to hold that and I would see it. Now we have the possibility of two people actually comparing at the same place what their watches are. And so what happens is this twin runs away, it flies away in his rocket, it has to go close to the speed of light. He turns around and then comes back, and now we can compare the two. And we haven't done the experiment, but we're very, very confident that this is what would happen, that one of them would be significantly older than the other. But what we have done is experiments on particles. And in the upper atmosphere, there are particles created by cosmic rays. They're called muons, and they only live for about 2/millionths of a second. And they're moving at about the speed of light. We can create them in different contexts, but we know that they live for about 2/millionths of a second. So 2/millionths of a second going at the speed of light corresponds to about 600 meters, something like that. So these muons that are created in the upper atmosphere, we shouldn't see them down on Earth, down on the ground, because they should have decayed before they reach the Earth, and yet we see them. They live longer. They live longer than we expect them to. And it's because they're moving at close to the speed of light. What's the big deal? Why does it matter if the neutrinos that are being observed in the OPERA experiment coming from CERN are actually going faster than light? Why does it matter? I could imagine that I've got a tachyonic gun that fires a bullet faster than the speed of light, and it goes bang. It has some speed greater than c, the speed of light, and it flies off and it kills the individual. There's no problem. The big deal is that I can change my frame of reference. I can run past this experiment quickly. I can run at a speed approaching light, but lower than the light speed, and the perception of this experiment will appear to that person to look like this. So viewed from a different frame, and remember, democracy of frames means that everyone's opinion on this is valid. What happens is that the chap would fall down dead before the bang. There'll be this causal reversal if the bullet was going faster than the speed of light. I can't convince you of that mathematically. I'd need to sort of do a bit more mathematics, but that's the essence of that. That's why it's a big deal. That's why physicists would be profoundly disturbed if these experiments were correct. Time and relativity becomes important when in gravitational fields, and clocks at the top of mountains run at different rates to clocks at the bottom of mountains. I did a calculation when I was preparing this slide, and at the top of Everest it'll tick. A clock at the base ticks 1 second minus 1 picosecond, whereas the one at the top goes 1 second. So the differences are very, very small, but they're important if you're a GPS system and you want to get your position accurate. We have this idea in physics, this idea of time being a coordinate. It's not the same coordinate as space, and it has different aspects, but this sort of amorphous grid, if you like, we can call space-time. And people that work on general relativity, I've done a bit of work on general relativity, actually try and manipulate this in their theories, try to look at what happens on scales that are much different from our everyday scales. And so the cosmic questions are, what is the shape of the universe? What is the fate of the universe? That kind of cosmic question. And we can explore different geometries and topologies and shapes of this sort of space-time continuum. And we can ask questions like, can wormholes exist? And wormhole is a way of taking a shortcut from here to some distant star. And in some sense, it's a mathematically consistent picture that comes from the equations. The trouble is that any attempt to actually make this is quite out of the question with current technology. But the idea is a sort of physically cogent development of Einstein's equations. The trouble is that any attempt to go through these throats and these wormholes appears to be doomed to failure. So calculations suggest that were you to actually attempt to go through this, you'd actually introduce too much disturbance, and it would actually pinch off this throat, and you wouldn't actually get through it.